Welcome to my vlog on big data and cybersecurity. My name is lipyeow-sec. I'm a computer scientist, an educator, and a software engineer. Today, I'm going to be talking about graph analytics without a graph database. This is not a well-known fact, but you can actually do graph analytics using data in the Delta Lake in Databricks without using any graph database. I'm going to show you how. So we're going to be using Okta logs and Azure AD logs, and we're going to be doing schema-on-read, meaning that we're not going to materialize the graph data model at all. We are going to extract the edges on the fly at query time. We're going to aggregate the edges on the fly at query time for data reduction, and then pass that off to graphframes, which is a package for graph algorithms that can work on very big graphs. And we're going to be using the breadth-first search and the connected component methods from the graphframes package. Now, this is the recommended analytics workflow, right? We're going to extract the data from the raw logs using a views, extract the edges, aggregate them, and then you're going to apply additional time filters and additional node and edge filters to extract the most relevant subgraphs to pass on to your graph algorithms. And from there, you can do reachability analysis using BFS. You can do impact analysis using connected components. You can do more advanced AI and ML stuff using graph embeddings and other machine learning models. And these types of graph analysis are really useful because you can do all sorts of lateral movement analysis. You can do, again, blast radius type analysis using just BFS and connected components. Let's take a peek at the data. This is the Okta logs. Again, nothing surprising. We use a very basic schema with just the ingest timestamps, the metadata, and then the actual logs are actually stored as a string, and this is the JSON straight from Okta. AD logs is the same, very similar schema. The raw logs are stored as a string, and they are just the JSON from Azure AD. Now, the views for extracting the edges from the Okta logs, this is what it looks like. I will have a separate video to explain the logic for the edge extraction, but this is the query to do it. And these are what the edges look like. Edges are essentially subject, predicate, object, triples. And you can see them here. I do store predicate status for like sign-in success or sign-in failure. And I do slap on a event timestamp. And from there, we can do aggregation based on time buckets. In this case, I'm using time buckets of a day. And basically, all subject, predicate, and object of the same day will get collapsed into a single entry. And this is what the result looks like. You have a time bucket, and then subject, predicate, object, and you have first seen, last seen timestamp, and the count. These three fields will be very useful when you're doing investigations. Now, we'll do the same for the Azure AD logs. I'm not going to go through those. Do the same aggregation view. And then this is the statistics that we get. And you see that the Okta data set is very small. The Azure AD data set is much bigger. And you can see that the aggregation by time buckets of a day actually shrinks the data down from 360,000 edges to about 15,000, which is very significant and will be very useful to speed up your analytics. We then create a view to union all the edges from different data sources together. In this case, we just have two. And now it's time to do some analytics. So we're going to do reachability or path analysis using breadth-first search. And the premise is this. Suppose you have two compromised nodes, and by nodes in the graph, this could be two compromised credentials for two email addresses, for example, email IDs. And what you'd like to find is, are there any paths between the two? Are they connected? And you would like to then see, are they from the same threat actor? Could it be a lateral movement from the same threat actor? And so you want to pull out the paths. Now, how would you do this? Well, first, we're going to use a query to extract the views, to extract the subgraphs, essentially the vertices and the edges. So for the vertices, I extract the subjects and the objects, union them together. I do apply a time filter, In this case, I'm not applying any node or edge filters because everything is relevant. And I do the same for the edges, except that I do duplicate the edges because I do want to do undirected path finding, in which case I need to look at the reverse edges as well. So I do the ref dash concatenate with the relationship to represent those. So once I have the vertices and the edges in their own data frames, this is what they look like. I will then pass them off to graphframe. So graphframe will create a internally a data frame like object that represents the graph. And then I just call the BFS method. I give it the filter for the starting nodes, in which case, this case is Megan Chang at changfisher.com. And the filter for the ending nodes, this is Maria Cook at summers.info. I do specify a max path length, and this is a good practice just to make sure that your path traversals are contained. And after about 2 minutes of runtime, it comes back with the results. And this is a table of paths. Each row represents a path. And let's just examine the first row, and that will give you an idea of how to interpret this result. So you have the from node, and this is Megan Chang. And then the first edge is a sign-in relationship, and it signs into Office 365 Exchange Online. And then we have another edge that is a reverse sign-in, and it's reverse sign-in from a Heather Martin. So it's an identity. And then that identity is related to an IP address with users. It relates to this IP address. And that IP address is then related to, again, reverse users to Maria Cook at summers.info. So now we have a path that, hey, actually Maria Cook uses the same IP address or machine as Heather, and Heather uses Microsoft 365 Exchange, and that is a common app or resource that was also used by Megan Chang, and that's the path. And so this could be the path of lateral movement, and this would then help you to go to deeper investigation into each link in this path. And obviously you have many paths here, and you can apply additional predicates to sort of zoom in on the most relevant paths that you might want to explore first. So this was breadth first search, and let's move on to impact analysis. So for impact analysis, what you are interested in is this. It's that suppose you have a compromised node. In the worst case, what is the blast radius? Suppose the threat actor via this compromised node can get access to all other nodes. What is the worst case scenario? What is the blast radius? What is the impact? And the way to do this is not to use recursive graph traversals, but is to use connected component analysis. What connected component analysis does is that it will break the graph into components or subgraphs that are fully connected. And let's actually take a look how this is done, right? It's very simple. With the same graph G, I just call connected components method. And after, again, about 2 minutes, it returns me with a table, which is a list of nodes with a annotated component ID. Now, let me show you how to actually use the results here. And with that, I actually printed out the number of connected components and the nodes in each component. And in this case, it's a very simple case. We only have one connected component, means every node is connected, and there's only one connected component, which means that, hey, every node is going to be in the impact zone, in the blast radius. Now, if you have two connected components, then if a node in component 0 is compromised, potentially everyone in component 0 is impacted, but component 1 will not be impacted. And so all the nodes there will be safe. And this is how it works. And this is pretty cool, right? We didn't use any materialization of the graph data model, and yet we're able to do graph analytics, pretty fancy analysis. And that's it for today. I'll deep dive a little bit more into some of the details in the next episodes.